Hi, this is Tom in the shop. I want to welcome my new subscribers. I really appreciate your interest. And this video is about, really it's a progress update on the Gear Hobbing Differential Mark II, which I've already described in a couple of videos and shown some math and so on. So this video is mostly short videos and still photographs, and there's a section on math at the end that's about 12 or 13 minutes long. So that's a long thing, but in the end I was trying to answer a couple of questions that I had gotten about how the differential system interfaces with the rest of the machine. So I hope that's useful. It's not necessarily something that everyone's going to want to watch, but it's there for anyone who's interested. Well, this is Differential Rev 2. This is the setup that when I finally understood the math, kind of suggested itself to me. And unlike the old setup where I had the two input legs tied together, this has the input, or actually the output, tied to the drum with a 28 to 60 tooth compound gear right there. And that's the ratio that, according to the math, should give me a 37 to 7 ratio between these two gears here. Just a simple illustration of how to produce an eccentric bore. I'm not really too particular about how much eccentricity there is. I'm shooting for about plus or minus 10 TIR. That's a piece of 16th thou brass, but you just put it under one jaw like that. And I turn the bore on center, put the thread in for the retaining screw. The bearing goes in there, and then when I turn the OD, I'll take that out and turn the OD parts and threads concentric to the outer diameter. Well, this section right in through here takes a look at the development and design of the new gear plate. which is going to support fixed centers instead of sliding centers, which is a big improvement from my standpoint. And I'm hoping that it'll be a good addition to the machine. There's a little bit more detail about how this layout came to be in the section on math that comes later in this video. Well, here we are at the CAD station. I just wanted to take a couple of minutes to try to answer a couple of questions that I've gotten. Good questions about how the differential hooks into the rest of the gear hobbing index train. If you watched the last little math mini lesson, we ended up at this point for a 37 tooth gear. We had A over B, or B over A, which is the inverse of our differential ratio. A is the tooth number, B is the output gear turns, and then these three compound gears complete the gear train for my machine, which has a machine constant of 90. And I'm going to try to kind of walk through the system piece by piece and try to help you understand how this works. I think the first thing I wanted to do was explain some of the choices that I made. If you recall the way the differential works or looks, we created this little diagram where A and B kind of represent the wheels on your car and C is the drive shaft, which I called the drum. And we built a gear train between C and B that has the ratio C over B, which we can decide. We can determine that ratio. And the way we do that is with an equation that starts out as C equals A plus B over 2. In other words, C is the average of the rotations of of A and B. And then we can solve that for A equals 2C minus B. And we can divide that equation by B to get the gear ratios, so we get A over B equals 2 times C over B minus 1. And this is how we can determine the ratio C over B for a given A over B ratio. Now, if you remember the equation or the numbers that I picked for a 37 tooth gear, if I just write this with the actual numbers, it's 37 equals 2 times 15 minus 7. So I picked 15 for C and minus 7 for B, and that 15 to minus 7 ratio is my C to B ratio. And once I express that as a ratio, I can also use that as a tooth count, because the tooth count is proportional to the speed ratio. And what I did then was multiply numerator and denominator by 4 to get into a workable range for me, and that's 60 over 28. And that's the ratio that I actually built into the prototype differential cluster phase 2. Now, a couple of things to understand about this. The compound gear that's involved in the train, a way to think about this is that the choice of B determines what comes downstream. So if, for example, let's write the equation or the relationship up here a little bit differently. Overall ratio equals 60 over 30 times B over A times 90 over 30 times 60 over 28. And all I've done is just rearrange the terms here, but basically what this boils down to is this is the input side of the differential in my terms. So I put a 2-to-1 ratio on the input side between the spindle and the differential. And this represents the output side, the 90 over 30 and the 60 over 28. And because, so let's just look at some different numbers and see how the choices we make change that gear train. So let's look at, say, 52. Using this equation right here, 52 equals 2 times I'm doing this on the fly. 2 times 22 minus 8. So that ends up being 44 plus 8. Now, I couldn't use 7 here because 52 minus 7 is 45, and that's not divisible by 2. So you can't really do that and make the math work out. Because you're always going to end up with an odd gear pairing in there somewhere. At least as far as I've been able to think it through, I haven't been able to come up with a way to make that work. So if I do 51, that's 2 times 22 minus 7. So when you consider that the ratio that affects the actual ratio of the differential is this one right here, this C over B. So in this case it's 22 over 7. In this case it's 22 over 8. This produces the result that we want, which is a 52 to 7 ratio. So B always represents the output of the differential. So it's either 7Z over 7 or Z over 8. So the rest of the gear train, and I mentioned this in the last video, the rest of the gear train stays the same except for that gear right there. And the way I have this set up, I have 2 ratios, one that I use for odd numbered gears and one that I use for even numbered gears. And there may be a cleverer way to set this up. I make no representations about that, but basically, if you remember that B is the output of the differential, then basically for every tooth number that you're trying to cut, where you can use a 7, assign B equals 7, the gear train stays the same. Everything stays the same except the differential. For every one that requires an even number and you use 8, all this stuff stays the same except that 28 is replaced by a 32 tooth gear for even gear. So this is a real simplification of the overall gear train, and again, all the action occurs right here in the differential. So let's set that aside for a second and look at what this means for the gear train that I'm actually working on. This is a diagram of the drawing actually. So imagine you're looking at the back of the machine. This is the spindle, and it rotates clockwise. This is the output gear, and that needs to rotate counterclockwise for my setup. And this is the differential center line. So the differential core is aligned with that point there. And all this stuff out here, all this stuff, the banjo plate and the gear clusters and the compound gears and all that stuff, the idlers and all that jazz, is focused on serving the differential, which is located here. Then, so this is the input train, and if you remember, I said I had a 30 to 60 2 times speed increase in the differential train coming into the differential. So here's that. That's the spindle. There's an idler which don't change the speed, and then there's a 30 to 60 compound here that feeds the input of the differential. Now the output is on B, and that's concentric to the rest of the differential. And we said a 90 to 30 and a 60 to 28. Those are both speed increasing compound gears. So here's the output gear on the differential that goes to an idler, which happens to be 60 teeth in this case. And here's my 30 to 90 or 90 to 30, depending on how you want to look at it. 30 tooth on the inner, 90 tooth on the outer. And then here is my 28 to 60 compound gear, and that's driving the output shaft. Now the reason I need to have so much speed up in my train is because I have a 90 to 1 rotary table as my final work holding solution. So I need a lot of speed in the output. When I redo that, I think I'm going to make a new spindle, a custom spindle, that'll be something more like 20 to 1 or 40 to 1. And I can accommodate that by changing this compound right here. I've already worked out the calculations on that. But, so that's the layout of the gears. Remember, almost all the action takes place in the differential cluster. So all this stuff can stay the same. The input side never changes. The output side, I'm just going to make a very simple transmission here that will allow me to shift between a 28 to 60 compound and a 32 to 60 compound, depending on whether I'm making an even or an odd gear. And what makes this possible is the fact that I get to pick what the differential output rotations are, what the output speed is relative to the spindle. That's what I'm doing with this. So by picking B equals 7, I use a 28 tooth to 60 tooth compound. By choosing B equals 8 for even numbered gears, I use a 32 to 60 compound. So that's how the system hooks together.